Okay, so physics extra help is what this is. I've had a request to do number 33, which is the one with the light hanging off the end of a beam, and then 36 and 37. A few people had a problem with 35, but I think once I said both billiard balls have the same mass, I think that fixed a lot of it for you. So number 33 on page 501 is a 24 kilogram light fixture is hanging from a uniform 3.5 kilogram horizontal beam. So the mass of the light is 24, the mass of the beam is 2.5. And the beam is 1.6 meters long, so the length of the beam is 1.6 meters long. Sorry. Wait, Autumn, shut up. A supporting cable makes an angle of 33 degrees with the beam. All right, and they draw a little picture of that for you. So the light's hanging here. There's the light. Looks like a shower more than a light, but anyway, 33 degrees here, and the full length of the beam is 1.6. And here's the pole that everything is hooked onto. And it says find the tension in the cable. So when I find the tension in the cable, I do that using the idea of torque. So when I think about torque, I have to think about all the forces that are working here. And there is, I'll call it the force of, I'm just going to look and cheat and see what I called it in my notes. I didn't really call it anything. I called it the wall. You could call it the beam, not the beam, the pole. I don't care what you call it. Let's call this the wall. It's not really a wall, it's a pole, but we have the force of the wall in the x direction, the force of the wall in the y direction. We have the force of gravity on the beam, and that would be pulling down in the center of the beam. Now here's the part that probably threw a lot of people. In the last one, the sign was centered on the beam, which means the force of gravity of the sign was also happening at the center of the beam. But this time, all of the mass of the light is down here at this end. So the force of gravity on the light is actually happening way down here because that's where the light is. It's not dispersed along this beam. It's all right at the very end. And then we have the force of tension of the cable, and it's going that way. So we have, and again, this is sort of what we think about as the pivot or the hinge point. This is where we're basing our R off of. How far away is the force from this point right here? So if we're thinking about torque because of the wall on the X, we're also going to think about torque of the wall in the Y direction. We're going to think about torque because of gravity on the beam. We're going to think about torque because of gravity on the light. And we're going to think about torque because of tension. And it's all got to equal 0. Now, these two are automatically 0 because those forces are happening right where that hinge point is. So they're automatically 0 because the R is 0. So thankfully, those are just gone. So really, I only have 3 torques left that I have to deal with. The torque on the beam because of gravity on the beam, well, that would pull the beam down, which means it would end up going clockwise, which is negative torque. Same thing with the light. It would pull it clockwise, so that would be negative. Tension would pull it counterclockwise, so that would be positive. Now, torque is R times force, lever arm distance times force. And remember, lever arm distance is always perpendicular to the force. So in this one, my R is the distance from where the force is happening, which is halfway down the beam. And so if the beam is 1.6, then my R is 0.8. And the force is gravity, so that is mass. Mass of the beam is 2.5 times gravity, which is 9.81, minus. Then we have torque of the light. Now again, my R is not going to be here at the center. It's actually going to be here at the end. Hello, Wicket. That's the wrong direction. Wicket. So that's actually 1.6 because it's the full length of the beam, not halfway. Stop. Stop. Come here. Yeah, come here. All right, and then, yeah, just calm your hormones. Just calm. Yeah, everything calm. And then the mass is 24. Sorry, I lost my place. And then gravity is 9.81. Plus, here's the little bit more complicated one. Force of tension, I don't know, so I'm just going to leave that as unknown. But I got to figure out my R. I left quite a bit of space for my R. I did that on purpose. Your R is perpendicular to your force. So it is the distance from the hinge point to the force of tension, but it has to be, well, that was a great straight line, has to be perpendicular to. So this is my R. So I want to know the opposite side, and I know that this length is 1.6, and that's my hypotenuse. So if I want to know the opposite, that is sine. So sine of 33 would be R over 1.6. So 1.6 times sine of 33, that would be my R. All right, so now the only unknown is my force of tension. So you can look through there and see which of your values you did not have right. My guess is you probably didn't have this one right, or you didn't think about the fact that it had to be perpendicular and you just used 1.6 as your R here. Those are the typical mistakes that I see. So when I solve for this, I got that force of tension, and I'm just cheating here, was 460 is what I got. I got 460 newtons when I rounded it off for significant figures. All right, so the next part of that question said find the force exerted on the beam by the pole. So that's this stuff over here. So I have to look at it in components, x components and y components, and then I can do Pythagorean theorem and I can do tan in order to figure that out. So I have to figure out FWX and I have to figure out FWY. Now you could call it FP for force of pole. I just chose W because that's what I had used in the other example. Doesn't really matter. So if I'm going to do that, first of all, I have to look at, if I do my WX, the only force going horizontally is this one in that direction, and that would be considered, for me, the positive direction. There is no force going this way, except force of tension is going at an angle. So it would be the force of tension, the x component, all right? Now, just so you know, force of tension, I told you a minute ago, was 460, but that was actually rounded off for significant figures. It's actually 463.8 to be more accurate, which is what I'm going to use in my calculations. And that has to equal 0. Now this FTX is going this way, so I'm going to do a minus. So again, thinking here, all right, we're going to be, we know that force of tension now is 463.8. We know that this is 33 degrees. And so we want to figure out, and actually, this isn't what we're looking at anymore. This is what we're looking at. Let me just, if I could make that more of a triangle. This is what we're looking at. This is my 463.8. So if I'm looking at the x component, that that is the adjacent side. So I would be doing cos of 33 is my adjacent side, which is my x, over my hypotenuse side, which is 463.8. So that means FWX, and I move this over here, it's equal to FTX, and FTX would be 463.8 times cos of 33. If I put you down, will you lay down? If I put you down, will you lay down? Probably not. Okay, and so when I did that, I got 388.98. All right, so then I looked at the y components. The y components in terms of forces, if I consider down negative and up positive, there is the y component here minus the force of gravity on the beam minus the force of gravity on the light. Those are the forces going up and down vertically, and that all has to equal 0. So the y component is equal to FGB plus FGL is what I get. And so, oh, I forgot one, didn't I? I forgot one. So, did you notice my mistake yet? Hope so. Those are not the only three. There's one other one. There is the force of tension in the wall. It's also going up, right? The force of tension on the cable in the y direction is also going up. So minus force of tension in the y direction, minus because if it was over here, it would have been positive. All right, so I missed one, sorry. So the y component then is the force of gravity of the beam, which is mass, which is 2.5, times gravity, which is 9.81, plus force of gravity on the light, which is 24 times 9.81, minus the y component of the force of tension. So this time I'm looking for this, which is the opposite. So it's going to be 463. I'm running out of space, so I'm just going to write it down here. 463.8 times sine of 33. So I do 2.5 times 9.81 plus 24 times 9.81 minus 463 times sine of 33, and I got 17.17. Hopefully that's what you get too. I'm cheating because I'm holding a dog and pressing buttons on a calculator would be difficult. So then if I want to know the overall force on the pole, I'm going to do Pythagorean theorem. I'm going to do 388.98 squared plus 17.17 squared, and then I'm going to take the square root of the whole thing, and I got that force on the pole was 390 newtons once I paid attention to significant figures, and I need an angle. So it would be tan of theta is y over x. And so my y was 17.17 over 388.98. And when I did that, I got 2.5 degrees. Now in the last one we did, it ended up that the angles were equal, and I said that would happen, but that happened because in the last one the sign was balanced in the center of the pole. The fact that the mass is at the end of the pole changes everything. So that's why it's not exactly the same as this 33-degree angle. That's why it's different. All right, so that's number 33. Yay. These questions aren't long at all. Okay, I'm going to put you down. No spinning. Stop. All right, and then 30, I think it was 36 and 37. Yeah, 36 and 37 was the other questions that I had. All right, and so 36 and 37. 36 says we have a bowling ball that has a mass of 6 kilograms. So we have a mass of a bowling ball that is 6 kilograms. And it rolls with a velocity of 1.2 meters per second. So the first velocity is 1.2 meters per second. Love my dogs some days. Hey! And it goes towards a single standing bowling pin that has a mass of 0.220 kilograms. So the mass of the pin is 0.220 kilograms. And the initial velocity of the pin is nothing. I hope they don't have moving bowling pins. That would make much more of a challenge. When the ball strikes the bowling pin, the pin flies off at an angle 70 degrees counterclockwise from the original direction of the ball. So I always make the original direction of the ball just straight like this, okay? So the ball's going this way. And let's say here's the bowling pin, all right? When it hits the bowling pin goes off at a direction 70 degrees counterclockwise from the original direction of the ball. So if the ball kept going in its original direction, it would go like this. However, the bowling pin, when the bowling ball hits it, flies off this way at 70 degrees from counterclockwise from the original direction of the ball. What was the velocity of the bowling ball after it hit the pin? Oh, sorry. It also gives a velocity of the pin of 3.6. So final velocity of the pin is 3.6 meters per second. And we want to know the final velocity of the bowling ball. That's what we want to know. So again, we have to break this out into components. We have to do X components and we have to do Y components. So we will do X components first, all right? And the momentum before is equal to the momentum after. So the momentum of the bowling ball times the velocity of the bowling ball. So again, we're doing before plus the mass of the pin times the velocity of the pin is equal to, now shut up, now we're going to look at after, and that's going to be the mass of the bowling ball times the velocity of the bowling ball plus the mass of the pin times the velocity of the pin, all right? So we know that the pin goes off at 70 degrees at 3.6 meters per second. Now what I said was, always draw your triangle down to your x-axis. So if that's 70, this has to be 20 degrees, all right? So here is my x component, here is my y component. So when I figure this out, mass of the bowling pin times velocity of the bowling pin before in the x direction. Well, the velocity of the bowling pin is 1.2, but that's all going in the y direction. It's not moving left or right. It's going straight, hopefully, if I can bowl at all. It's going straight down the alley. It's not going left or right. It's going straight down the alley. So what that means is that my mass is 6, but my velocity is nothing. Plus, mass of the pin is 2.00, but before the ball hits it, it's not moving. And so afterwards, the mass of the bowling ball is still 6. It hasn't lost any mass, and we don't know what the velocity is. And remember, we are looking for the x component in this, plus mass of the pin is still 0.220, but velocity of the pin is not simply 3.6. We're looking for the x component. So that's the adjacent over the hypotenuse, so that is cos. So I would be doing 3.6 times cos of 20. Now, in my text, not in my textbook, in my answer key, I actually have that my velocity is negative 3.6 times cos of 20 degrees. That doesn't look like an anything. Times cos of 20 degrees. I have a negative there. The reason why I have a negative there is because when I drew this, this is a negative x component. That's why I made it negative here, because I know it's going in the negative direction based on my drawing. So this side is just 0, and that's equal to 6 VBX plus 0.220 times negative 3.6 times cos of 20 degrees. Even if you got everything, if you didn't put that negative there, it would throw everything off. And so what I got, when I moved this over to this side and divided everything by 6, I got that my x component was positive 0.1240. Positive 0.1240. So I'm going to write that over here. VBX is 0.1240, and that's positive. So that's my x. Now we're going to do the y. Same formula, before and after, but now we're going to look at the y components. So mass of the bowling ball is 6, velocity of the bowling ball. Well, all of the velocity is going in the y direction, so that's 1.2, plus mass of the pin, which is 0.220, but the pin's not moving, is equal to mass of the bowling ball, which is 6, times the y component of the bowling ball, plus mass of the pin, which is 0.220, times the velocity of the pin. But remember, it's the y direction, so that is sine. But the y is positive because it's going up. It's in the positive section for y. So I'm going to make my 3.6 positive times sine of 20. Wicket, come! All right, so this is 0. So I'm going to have 6 times 1.2. I'm going to subtract all of this because I'm going to bring it over and subtract it, and then I'm going to divide it all by 6. Wicket! And so when I figured that out, I got a positive 1.15. So VBY is 1.15, and it's positive, which means if the x is positive and the y is positive, which means it's the bowling ball's going off in this direction in some way, which kind of makes sense. The bowling ball hits the pin flies off this way, the ball goes off this way. Just makes sense. I am ruining bowling for you. If you like bowling at all, the next time you go bowling, this is going to be stuck in your head. I'm sorry. So now we have this. So if we want to figure out the velocity is going to be, the total velocity of the bowling ball is going to be 0.124 squared plus 1.15 squared, and then take the square root. And I got 1.16 meters per second. Now they also want an angle. So tan of my angle is my y component over my x component, right? Because here's my angle, it's y over x. It's opposite over adjacent. So my y is 1.15, my x is 0.124, and so I got that my theta was 83.9 degrees. Now that is not the answer they have at the back of the book. I'm going to show you why. So that's 83.9 degrees, and that would be 83.9 degrees this way. So if I was giving it as a direction, I would say 83.9 degrees counterclockwise from positive x-axis. Because from the x-axis, the positive side, I would go 83.9 or 84 degrees counterclockwise. You could also give, and that's close enough to 84, so let me just round that off to 84. So if I looked at it the other way, it would be 6 degrees clockwise from the positive y-axis, which was the original direction of the bowling ball. So it's 6 degrees clockwise from the original direction of the bowling ball, because the bowling ball was going this way, and it goes off 6 degrees this way, because this angle is like 84 degrees, which means that one is 6. All right? So what happened, this isn't drawn accurately because I was guessing, but so what happened is the pin went off that way, and the bowling ball just kind of veered off a little bit, is what actually happened. So there is 36, and I'll do 37. I think it's similar, but I'm not sure. I actually haven't looked at it yet. Hold on. So 37 says car A is 1,750 kilograms. So the mass of car A is 1,000, and I forgot it already, 750 kilograms. And it's traveling due south. Alrighty. Car B is 1,450 kilograms. So it's a little bit lighter car. And it's traveling due east. They reach the same intersection at the same time and they collide. They lock together and they move off at 35.8 kilometers per hour east, 31 degrees south. So I'll just finish my little compass rose here. I'll finish my little Cartesian plane. And east, 31.6 degrees south. So from east, 31.6 degrees south. So the cars go off this way at 35.8 kilometers per hour. Okay. What was the velocity of each car before they collided? So I want to know what was the velocity of A initially and what was the velocity of car B initially. So we're basically now accident reconstructionists, because when you come on an accident and two people are sitting there and they've just been in an accident, one person is going to go, he was going so fast, he was speeding, he came out of nowhere, and the other guy's going to say, I wasn't speeding at all, you were the one who was speeding. They have to figure out who's telling the truth, who's lying. Maybe they both were speeding. I don't know. So that's what we have to figure out. Now, there's good news about this. And the good news about this is that you actually don't have to convert this kilometers per hour into meters per second. The reason why you don't have to is because momentum is mass times velocity, and it doesn't have its own unit. Like, it's always kilograms times meters per second. But as long as all of your velocities are in the same unit, it actually doesn't matter whether you use meters per second or whether you use kilometers per hour. As long as they're all the same unit for momentum, it doesn't actually matter. So we're going to leave it in kilometers per hour because that's going to be easier. All right, so here is what I would do. Again, I'm going to break this up into X and Y components. So let's do the X component first. Oh, and by the way, this is car A was the one going due south, and car B was the one going due east. All right? All right, so here we have our little triangle here. So let's look at the X direction first. So it will be mass of A times velocity of A plus mass of B times velocity of B is equal to, now again, here's the trick. It very clearly said that the cars lock together, all right? So it's not like one car goes off in one direction, one car goes off in another. They lock together, become one thing, and veer off here. So that means I don't have two separate momentums on this after side. I only have one momentum. I have the momentum of the two cars locked together moving that way. So if I'm talking about my X component, it's going to be mass of A and B together because they're now one thing, times the velocity of A and B together. So now let's fill in some of this. So again, we're only looking at the X direction. We're just looking across, okay? So mass of A is 1,750, but initially car A is only going south, so it has no horizontal direction. So its before velocity is nothing in the X direction. Plus mass of B is 1,450 times velocity of B. Well, all of its velocity is in the horizontal direction, all of it, because it's going exactly east. But we don't know what that is, so we're going to leave that as we don't know. That's equal to the mass of A and B added together. So I added 1,750 and 1,450, and I got 3,200. And velocity of A and B. Now remember, this is the X direction we're looking at. So we have to find the X component. So that's the adjacent side. So that would be cos of 31.6 is adjacent over hypotenuse. And so it would be 35.8 times cos of 31.6. I now only have one unknown, just this one. So this is 0. And so I'm going to figure out what this is, and I'm going to divide it by 1,450. When I did that, I got 67.3. And that would be kilometers per hour. And that would be going east because car A was going east. So velocity of car B is actually 67.3 kilometers per hour due east. So if they were in a 50 zone, this guy was speeding. All right, so then we have to do the same thing, but we're going to do it for the Y component. So again, nothing different, just the Y components this time. So before the collision, mass of A is 1,750, and all of its velocity is in the Y direction, so, and we don't know what that is. Plus, mass of B is 1,450. Now, velocity of B is all horizontal. There is no vertical movement, so its vertical velocity is 0. So then mass of A and B is 3,200, but this time we're looking for the Y component, so the only difference is now that is sine. So it's going to be 35.8 times sine of 31.6. Now, again, to figure this out, we just put all of that in. That's gone. And so we're going to figure that out, and we're going to divide it by 1750. Really, technically speaking, you could make this negative because the y is negative, but it really doesn't matter in this case because the negative is just going to tell you that it's south. That's all, and we already knew that ahead of time. So whether or not you make that negative there doesn't really matter in this case because we are already aware of the direction. So my velocity of A would be this times this times this divided by 1,750, and I got that that was 34.3 kilometers per hour, and that would be he was going south. So it looks to me like this guy wasn't going very fast, but this guy was going almost double his speed. So car B is much more at fault. So as an accident reconstructionist, when I'm reporting to the insurance companies, because the insurance companies are going to fight over who has to pay out, this is actually going to weigh pretty heavily into their decision. That's why we have stuff like that. All right, so I hope I answered all your questions. Don't forget you have an assignment due next week. I can't remember what day. I think it's Thursday, but I'm not sure. I kind of staggered everybody's. I've got like 4 different assignments coming in next week, so I staggered the due dates on all of them. I think yours is Thursday, but I'm not 100% sure. And again, if we don't get to the end, there is one question at the end that we haven't covered yet. We're getting there, but we just haven't gotten there yet. I think I have 2 more examples to do, and that's it. But you could certainly be working on the rest of them so that when we get to that last one, you just have that last one to do, and that's it. All right, hope that helped. Bye.